Hi, everyone. Welcome to this session on mathematical structures and in quantum foundations. And in the name of Shihan and Hai, let me thank all the speakers for agreeing to talk to us today. And I'll just say a few brief words. So, I mean, quantum foundations is kind of a subject that has sort of goes back to the beginnings of quantum mechanics and is somewhat an intersection of physics and philosophy, and to some extent more recently computer science and given sort of quantum information, quantum computation, and of course mathematics. And there's a lot of different sort of mathematical structures that come into this, from probability and convex geometry to logic, algebra, category theory, algebraic topology even. So I think we'll touch on some of those in some of these talks. And I guess in a sense the goal of this session is to give a flavor of what this field is about. And we have four great speakers that are going to speak to us about different subjects in their own work. And I think we should start without any further comments, because we have kind of very limited time slots. And our first speaker will be Ravi Kunjwal from ULB in Brussels. And he's going to talk to us about contextuality and zero-error communication. So Ravi, if you can...
Okay, thank you. I'm going to share my screen now.
Thanks.
Can you see it?
Yeah.
Okay, that's okay. Cool. Thanks, Hui. Thanks to the organizers for inviting me for this short talk in this session. I'm going to tell you about some work that I did with a summer student, Shiv. He's currently at Duke. I'm at the U of A. And this work is essentially brings together a bunch of foundational strands in quantum theory within this quantum information protocol called entanglement-assisted one-shot classical communication. Okay, so as I said, we're going to look at this particular task. And we're going to look at the role that different quantum phenomena play in this task. In particular, what's the connection of this task with non-local games, and how is this task connected to contextuality, both in the quotient-Specker sense and the Speckens sense, for those who know what that means. Okay, so this talk will be in two parts. In the first part, I'll just briefly introduce the concepts we're going to need, the bare minimum we need. And then in the second part, I'll tell you what the results are without giving you any proofs. Okay, so the task. So this is the basic setup. Like, we have two parties, sender Alice, receiver Bob. They share a classical channel, which is in general noisy. And Alice inputs some symbol to this channel, some input letter from an alphabet, and this letter is X. And Bob observes an output Y. And these parties, so obviously these parties are time-like separated, and we're allowed like one single use of a classical channel. It's not like a case of multiple copies of the channel being used. Okay, and so that's why it's one shot. A simple example of this task is, for example, just look at this channel. It has four inputs, so 2-bit inputs, and these are the inputs, the vertices in this hypergraph. It has 6 possible outputs. So these are the hyper edges. So it's completely connected. So every vertex is connected to every other. And Alice is going to choose some sort of encoding for the message she wants to send to Bob. So for example, here the encoding is of this type, where to encode message 0, Alice chooses these two symbols to encode 0. And to encode message 1, she uses these two symbols. Okay, so here, for example, the thing they share is the first bit. So the first bit tells you what the message is, right, of these two. So a message encoding in general is a partitioning of the set of input symbols X. And the channel probabilities are some, so this is the probability that you see output Y if the input of the channel was X. Okay, so this channel appears in this paper, where there's a particular implementation of this. And so for those interested, you can look at this, but I'm just using this as for illustration purposes. Okay, so what do we mean by entanglement-assisted one-shot communication? well, okay, before that, for the classical case, the success probability is obviously like, you start with, Alice starts with choosing some message to send with some prior probability. Given this message, she picks some symbol from her encoding for the message M with some probability. She inputs that symbol to the channel, and then Bob receives the output Y with some probability, and Y given X, given by the channel. And then given Y, Bob has to use some sort of inference strategy to guess what message Alice was trying to send. And so that's this. And so overall, the success probability looks like this. It's kind of obvious. So this is a convex picture of different possible strategies they could have, but in general, like, there is a one of the extremal classical strategies is the optimum one. Okay, so the second part of this protocol is like when you allow Alice and Bob to share a joint state and implement some local measurements on that state. Okay, and we are interested in whether, like, having access to this quantum resource allows us to do better at this task of sending messages across this channel. So in the general case, when you do allow entanglement, the protocol looks like this. Alice thinks of a message she wants to send. Depending on what the message is, she's going to implement some measurement on this entangled state, observe some outcome X, and this X is going to be input into the channel. Bob receives the outcome of the channel Y, and Bob will decide some measurement strategy depending on that. And then we'll use the results to infer what message Alice was trying to send. And they succeed if M prime equals M. And so in general, the success probability looks like this. So note that this is the piece that's where quantum theory enters in some sense, because this is the measurements that Bob is doing on his side. And the advantage is going to come from somewhere here. Okay, and so we have summed over those instances of M prime where M prime equals M. So that's the success probability. Okay, so yeah, so as I said, the information on Bob's side, so from the classical channel, Bob just receives Y, but because they share entanglement, there is this extra sort of conditioning here, given the conditional state that Alice steers Bob's system to. There is some probability for seeing some for Bob's outcomes given by the Bond rule. So so we're going to look at this object to look for the source of the advantage. Okay. The second piece in this three-part puzzle of the three aspects is non-local games. So now imagine a different scenario where Alice and Bob are space-like separated. So there's no communication from Alice to Bob in this case. There's no classical channel, but they're doing exactly the same measurements that they would do in the communication task. And they record outcomes just like they do there. And you collect some joint conditional probabilities. And you're interested in whether they violate a Bell inequality or not, whether they violate some classical bound. Okay. So this is the second piece. I didn't spend too much time explaining it. I'm hoping you can look it up if you don't know what these are. The third strand is contextuality, where we're going to look at, so again, this is the bipartite sort of setup where Alice is doing some measurements on her part of the entangled state, obtaining some outcome and sending the outcome to the channel, and the output of the channel determines Bob's measurement strategy, and then Bob will do some processing to get the guess. And on Bob's side, this basically Alice's measurements induce some preparations. So we want to look at the contextuality of the prepare and measure scenario on Bob's side in this situation where the preparations are remotely steered by Alice. Okay. Okay, and so of course, when I say contextuality, I have to first tell you what non-contextuality is, which is it's a notion of classicality that we use to sort of articulate what it means for some operational statistics to be classically simulable. So here, it's motivated by this idea that operationally indiscernible things should be ontologically identical. So so quickly, for example, you implement some preparation procedure P, followed by some measurement M, observe some outcome K. So this is the operational statistics you observe in the lab. Now the question is, can the statistics be simulated by a model where you imagine that the system that's passing between the two devices, so this, has some ontic states lambda. So P samples lambda according to some probability, and then the measurement device responds with some probability. Okay, and the average of this gives you the operational statistics. And so preparation non-contextuality here is the idea that if no measurement can distinguish the two preparations, then the preparations are ontologically the same. So in quantum theory, this is quite simple to see. So for example, maximally mixed state in a qubit, when you prepare in the Z basis, this is one particular preparation. Flip a coin, prepare spin up or down in the Z basis, or you can do it in the X basis. Both of these are operationally equivalent because they're the maximally mixed state. So that means by preparation non-contextuality, the distribution you associate over any sort of ontic states in any ontological model, I mean, a non-contextual ontological model should be the same. So it's only depends on the equivalence class, like namely the density operator. Okay. Measurement non-contextuality is again a similar idea that if no preparation can distinguish two measurement events, then the measurement events are ontologically the same. So a simple example is when the same projector appears in two different measurement bases in quantum theory. The Bond rule doesn't care which measurement basis it appears in, they're indistinguishable. So for example, the second outcome here is indistinguishable from the third. So we'll assign them the same response functions. Okay. So now that I've introduced the three pieces we needed, let me just quickly go to the results. So the first result is that the preparation contextuality of the system that Bob is holding is responsible for the quantum advantage, in the sense that if you assume that Bob's system has a preparation non-contextual ontological model, then the upper bound and the success probability in the task is the same as the classical upper bound. So it's tightly related to preparation. Contextuality is tightly related to an advantage in the task. Okay. The second thing is the connection between this communication task, where the parties are time-like separated, with this another task, which is a non-local game where the parties are space-like separated. So we want to connect an advantage here to an advantage here. And in fact, it is the case that a quantum advantage in the one-shot communication task allows us to show a quantum advantage in a corresponding non-local game. And so explicitly, we show this for a particular family of classical channels, where we show that when you have an advantage in the communication task, you're going to have an advantage in the non-local task. And of course, you have to design the non-local game in a particular way, which depends on the channel that you're working with here. So the non-local game is really tailored to the channel that you're using here. And yeah, of course, when in the case of perfect communication, like when you're able to have a success probability of 1, you win this game perfectly. And so this is a situation where quantum theory wins a Bell game perfectly. So in this paper where this result was shown, the second part, it's basically the pseudo telepathy games, for those who know what they are. So in this paper, so this is another example of a classical channel. It just looks much more complicated than the 4 symbol channel that I showed you initially. But the principle is the same. The vertices, the hyper edges, these dotted vertices have the same interpretation. Classically, this channel can be used to send 5 zero-error messages. But quantumly, you can show that given access to a maximally entangled state of 2 4-level systems, you can actually send 6 zero-error messages. Okay. So the idea here, okay, let me just quickly tell you what we do with this protocol. So we generalize this sort of protocol from pure situation, which is applicable to pure measurements and states, to allow for noise. Instead of looking at the increase in the one-shot zero-error capacity from 5 to 6 messages, we look at the one-shot success probability of sending a fixed number of messages, which is 6. And the original protocol, it has to do with quotient spectral contextuality, which is related to, so this is basically the orthogonality graph of a quotient spectral set in some sense, I mean, in a precise sense. And what we do is we generalize that to talk about preparation and measurement non-contextuality. So the first result in this case is, so of course we know that in the general case, preparation non-contextuality bounds the classical sort of success probability. But if you assume measurement non-contextuality, this means that you're restricting the response functions further. And then that means that in general, this expression will be less than this. So the question is, when is this upper bound saturated? So in this case, this happens when, so we motivate a particular constraint, which leads to this. So which is the idea that imagine a situation where Bob doesn't know or trust the channel probabilities. Bob only trusts the channel hypergraph. So only the combinatorial structure of the channel, but not the probabilities. And so in that case, Bob, in his inference, cannot really use the channel probabilities. He can only use the structure of the channel hypergraph. And this motivates this constraint of context-independent guessing, which is namely that the Bob's guess for what the input symbol was doesn't depend on the particular output symbol he receives. It only depends on like the set of output symbols that correspond to his guess. Okay. So essentially what we show, so the original protocol of qubit and others, it satisfies this constraint. We're just articulating that constraint more precisely. And so then under this constraint, the classical success probability is the same as the non-contextual upper bound. So the upper bound is the same. And then the main result here is that we can witness advantage in this task using a particular hypergraph invariant, this beta, which is a property of just the hypergraph, together with some distribution defined over its hyperedges, some of its hyperedges. And so this thing is a violation of a non-contextuality inequality. If this non-contextuality inequality is violated on Bob's side, then that means that Bob's measurements can be actually used to witness an advantage in the communication task. So in this sense, this provides an application of some noise-robust non-contextuality inequalities that were originally derived in this paper quite independently. So yeah, and I think that brings me to the end of the talk. So basically, these are our results. And yeah, I think I'm gonna end here. Thank you.
Thank you, Ravi. Sorry, I was muted. I'm just checking for the checking whether there's any questions on the website. Which is here. Don't seem to be any at the moment. So maybe one of the other participants has any questions here. Or, if not, right. So there's no question at the moment. Yes. So do you think? So I guess my question is, so what you seem to be showing here is that there's kind of a way of, well, I mean, so two things. So on the one sense, what you were saying is that that there is a result that was there for what do you call quotient spectral contextuality, which gets generalized to sort of preparation on contextuality. So the spectrum is kind of contextuality, and it goes from being sort of a sharp result or deterministic result into being a probabilistic thing.
Yes,
which is something that can also happen even within the notion of quotient spectral contextuality with things like non-state independent contextuality. Or is there a relation between the two kind of?
So the original paper was using state independent contextuality. Like that's what they were working with. So of course, like that's one of the actually open questions, which is. So that's this particular question that, what would this look like, for example, for generic classical channels? So the classical channels that we study are the ones which are uncolorable in the sense of quotient spectrum. So in the sense that you cannot pick an outcome from each measurement in a way that all the outcomes are mutually non-confusable. So this channel is quotient spectrum uncolorable. In fact, even this small channel, this 4 symbol channel, even this is uncolorable, because if you apply except the only difference between the two is that this one doesn't admit a quotient spectrum set. The other one does. And so when it does admit a quotient spectrum set, you have an ideal strategy that gives you a success probability of 1. When it doesn't admit a quotient spectrum set, then even then you can sort of sometimes draw connections with non-local games and show an advantage. So in this case, for example, in this paper, the authors basically sort of work backwards in some sense from the CHSH game. So they leverage the CHSH game to show an advantage for channels of this type. And so what we do is basically sort of combine all of these in one framework where we look at channels which are uncolorable in this sense. So your question, I guess, is more an open question for me at the moment, like how would that situation? So because we don't even have an example at the level of just the quotient spectrum level from which to generalize. So I guess maybe the first simple question would be, can you do it in the quotient spectrum case? And then, because the thing is that for the state independent case, it's kind of obvious that you can do, but it's not so obvious you can do it, but you can see the motivation because there's this Hayward-Redhead, I think, method of turning a quotient spectral proof to a non-locality argument. The pseudo telepathy games is what they're called in a lot of the literature.
Yes.
So this is related to that in the qubit paper. And what we do is we generalize that to other situations where maybe the quantum strategy is not perfect.
I see. Okay.
No.
Yeah, I probably would have a follow-up question relating to that, but maybe we should leave it to another time.
Yeah,
because,
we can chat.
We should move on. And now we have John.
I'm going to stop sharing.
Well, John Selby, could you share your slides, maybe?
Yeah.
And yeah, so John's going to give us a brief talk about generalized probabilistic theories and some of the tools that come into their study. I think maybe we should start straight away.
Okay, well, thanks for everyone for coming, and thanks to the organisers of this session for inviting me to give this talk. So yeah, I'm going to talk about generalized probabilistic theories. I'm going to try and have a sort of quick run through them and to try and highlight the various mathematical structures that come into play and to just highlight a couple of interesting results that have come out of this field of research. The basic idea behind generalized probabilistic theories, or GPTs, is to try and study physics without any pre-commitment to any particular physical theory, such as quantum theory, and to sort of avoid having sort of preconceptions about how we think physics should be as much as possible. So why should we do this? Well, I think one of the important reasons is to try and understand quantum theory itself better. So to say, okay, how can we understand the quantum theory? Well, one way is to understand how it could have been instead, and then to try and figure out what makes quantum theory special as compared to those other theories, and find out what features of quantum theory are, say, underpowering the information theoretic advantages of quantum theory. Another reason is that, well, quantum theory might at the end of the day be wrong, that nature might actually be some other physical theory. In particular, if we try and start reconciling quantum theory with general relativity, then there's good reason to think that we might have to change both of these theories. And I think finally, and maybe most importantly, it's just an interesting mathematical structure to play around with, so it's fun. This all sounds quite vague, so how are we going to approach this? How are we going to try and study physics in this way? Well, we take an operational viewpoint, which says that so the bare minimum that any physical theory is going to have to do is it's going to have to be able to make predictions, in particular probabilistic predictions, about the outcomes of experiments that we perform. And this sort of very basic idea, if you think about it hard enough, as, for example, Lucian Hardy did in this paper, you can show that you arrived at a very rich mathematical structure from this. Okay, so quick overview of the talk. I'm going to start from sort of a very low-level picture where I'm just looking at the states of a single system and the properties they have. And then I'm going to sort of zoom out and out through transformations between states to defining GPTs as a whole, and then to look at sort of the landscape of all possible GPTs. This is going to be a very quick talk, so if people are interested, then I highly recommend this introductory text that came out recently by Martin Plavla, which goes into a lot more detail and is really nice. Highly recommend it. Okay, so a couple of warnings before I get going. I'm going to ignore something called effects entirely in this talk, but luckily in the next two talks, these will be talked about a lot, so we don't need to worry about that. And I'm also going to make a bunch of simplifying assumptions so that I can make more concrete statements than I could otherwise. So don't take everything I'm saying as sort of complete generality. All right, so I said I would start from a small scale and imagine that we've just got some physical system and look at the states that that physical system can be in. So we call the state space omega, and sort of a couple of example states would be S1 and S2 living inside omega. And we don't just want some sort of arbitrary set of states, we're going to have some structure on it. So in particular, there should be a convex set. So if we think that we can take some sort of convex mixture of two states, S1 and S2, then really this is meaning that we have some sort of uncertainty about whether we have state S1 and S2. Maybe someone's flipped a coin and then decided, based on that coin flip, which state to prepare, but hasn't told you which outcome, whether it was heads or tails. It should also be closed. The idea being that if we can prepare some state in a lab arbitrarily well, then we may as well assume that we can just actually prepare that state. So this state F on the boundary is included. And it should also be a bounded convex set. And ultimately, what this means is that any pair of states within the state space can be distinguished from one another with some non-zero probability. And as I said before, finite dimensionality, but this is technical convenience rather than anything physically meaningful. So there's two different types of states. You've got pure states and mixed states. And the pure states are extremal in this convex set. The mixed states are not extremal, but some of them may lie on the boundary, such as S prime here, and some of them may lie in the interior. Okay, but any theory of physics has got to do more than just tell us what the states are. They've also got to tell us, oh sorry, before getting to that, I'll illustrate this with some examples. So the simplest example are classical state spaces, which are simplices. And we think of these as having the vertices as sort of deterministic states, the different set of states that a classical system could be. And then all of the other points in the simplex corresponds to states of knowledge about this. So probability distributions over these extremal states. Quantum systems, on the other hand, have states which are described by density matrices. So these are complex matrices that are self-adjoint and trace one. And in the two-dimensional case, these live inside the blocks here, depicted here. And there's a bunch of other examples that have been widely studied, such as real quantum systems, like this circle here, tree bits, which are used in the study of non-locality, and epistemically restricted bits, which are used in the study of contextuality. Okay, but as I started to say, we need to also talk about the way that physical systems can evolve, so we need to define transformations here as well. Transformations ultimately are going to just be some convex linear maps between these state spaces, omega and omega prime, which means that taking convex combinations commutes with transformation. And the intuition behind this is that any physical transformation should preserve our uncertainty. So if we don't know whether we've got state S1 or S2 at the start of the evolution, then we shouldn't know whether we've got state TS1 or T of S2 at the end of the evolution. And, okay, having this definition, we can then put all this together into a category we call conv, in which the objects in this category are state spaces, just arbitrary state spaces, and the morphisms are these convex linear maps. To illustrate this with some examples, if you look at the morphisms between these classical systems, these simplices, as I said, we can view these as spaces of probability distributions over some finite set. Then these convex linear maps really are just stochastic maps between these finite sets. We can also define measurements, which are convex linear maps from any state space omega to a simplex, where the simplex now we think of the vertices as being the different outcomes of the measurement. So any state S in omega will get mapped by M to some probability distribution over the vertices of the simplex. This is how we get probabilities out of the theory. This is how we get those probabilistic predictions. We can also define a trivial system, a trivial state space, which is just a single point in the state space, which I call star. And then it's easy to see that sort of the morphisms from star to omega are in one-to-one correspondence with the states of omega. And that if we look at the morphisms from omega to star, then there's actually just a single one of those. So there's a unique map to the trivial system. And this we think of as sort of a discarding map or just ignoring a physical system. Let's define a couple of useful properties of transformations. The first is a transformation is purity preserving if it maps extremal states, that's the pure states, to other extremal or pure states. And a transformation is reversible if it has an inverse. And reversible transformations are useful because they allow us to define the automorphism group for any state space, which is just the group of reversible transformations from that state space to itself. Okay, so one of the things we can sort of ask at this level of description is what makes the quantum state spaces special? What distinguishes them from all of the others? And there's a really nice partial answer to this question through studying these things called K-frames that was in this paper by Barnum and Hilbert. And I think in Alex Wilfer's talk, there'll be a lot more about this kind of stuff, so I won't go into detail here. But you can define a K-frame by a pair of transformations. One is a purity-preserving transformation from some simplex to omega, and the other is a measurement from omega to the simplex. So this measurement is the left inverse of f. So this is t here, so it should be an f rather than a t. And then you can define, using this notion, a couple of important properties of state space. The first is spectrality, and the second is strong symmetry. But if your state spaces satisfy these properties, then you can show, or they show in this paper with quite a lot of work, that the state spaces are either finite dimensional simple Jordan algebras or they're simplices. And this is remarkably close to the quantum state spaces. There are examples of these simple Jordan algebras. And these principles of spectrality and strong symmetry can be motivated from physical ideas, so they're very natural. So in some sense, this takes us through very natural ideas to something that's very close to quantum theory. And the key tool underlying this theorem is a classification of regular convex bodies by Madden and Robertson in this paper here. So as I said, I think Alex will go into more detail about this kind of research line, so I won't go into more details here, but I think this hopefully motivates the kind of questions that you can ask from this perspective. But let's now try and define a GPT. I've talked about this category with state spaces and convex linear maps, but in any physical theory, we don't expect every possible state space to correspond to some physical system. So instead, what we expect to get is some sort of subcategory of conv. So some sort of collection of state spaces that correspond to the physical systems that we believe exist in this particular physical theory. In particular, though, whatever subcategory we have, it should include as objects all of the simplices, because these represent our classical interface with the microscopic world. They represent sort of the control variables or the setting variables and the outcomes of experiments. And then we have a couple of consistency conditions, which say that really the interaction between this classical interface and the other systems, the other omegas that we have in this subcategory, should be unrestricted. So to give an example, we can define G delta as the full subcategory of conv where the objects are all of the simplices. And this really represents sort of classical probabilistic physics. In particular, you can quite easily see that this category is equivalent to category stock, where objects are finite sets, morphisms are stochastic maps between them. And given these consistency conditions I talked about above, it's quite easy to see that this must be a full subcategory of any other GPT. So any other GPT contains this sort of classical model of physics within it. Okay, but something very important is missing from this, and that is the idea of a composite system. So if our physical theory includes some system omega and another one omega prime, then it must also include some system that describes the composite of these two. And we're going to denote that by this box times symbol. And if you think about this for a while and think about what this means physically, then you come to the conclusion that this means that G should actually be a symmetric monoidal category where box times is the monoidal product, and the monoidal unit is going to be given by this trivial system, just a single point. But we want sort of the classical part of whatever theory we have to still behave in the way we expect classical physics to behave, which means that on this subtheory, G delta, we expect box times to coincide with the standard tensor product for stochastic maps. And given this, you can show that whilst box times is not going to be something that is uniquely defined, like there's lots of different ways you could choose how to compose systems, which is one of the things that makes GPTs an interesting theory to study, you can still show that they're going to have to be bounded. And particularly they're going to have to be bounded between the so-called min and max tensor products, where the min tensor product is a set of all separable states, so those that can be thought of as product states and convex combinations of them. And then the max tensor product gives you the biggest possible state space that is compatible with your theory having product measurements within it. And what's interesting is that when you look at simplices, then all of these different tensor products coincide with one another. And what this means is that really there's no way to have entanglement between simplices. There's no way to come up with some alternative physical theory where simplices have entangled states, so they're unentangleable, we could say. This naturally leaves the question of, okay, well, simplices aren't entangleable, but which convex sets would be? And there's some really nice work recently in this direction. So to just give a definition, we say that two state spaces, omega and omega prime, there should be a prime here, are entangleable if and only if the min and the max product are distinct from one another. And way back in the 80s, albeit in a kind of different language to this, it was conjectured by Barker in this paper that the only the only way that two state spaces are not entangleable is if one of them is a simplex. And very recently, only 2 years ago, so some 40 years after that original conjecture, this was proven by Oberon et al. In this paper. And this was a really remarkable result that involved lots of ideas coming from GPTs as well as coming from algebraic topology. And so what this means is that any pair of non-simplicial state spaces can be entangled within some GPT. Not necessarily every GPT, but in some GPT they will be entangleable. Okay, so another nice thing that comes from this viewpoint of GPTs as symmetric monoidal categories is that we get this diagrammatic representation coming from string diagrams for symmetric monoidal categories. In this sort of depiction, systems are represented by these wires, and morphisms are represented by these boxes. And what this really represents is just some sort of description of composition of different morphisms within the symmetric monoidal category. So in particular, this, at the end of the day, is going to have to be equal to some other morphism. In this case, some convex linear map from delta n to omega box times delta m. So this is, I won't go into this in detail, but this is just a very useful depiction for these things. And in particular, we also represent convex mixtures in a very natural way here as well. So if this morphism F was actually a convex combination of some FIs, then we can represent that in the diagram. And because everything is convex linear, we can just pull those sums out of the diagram as well. So really, we don't need to bother drawing these dashed boxes. The sums are unambiguous. Okay, so that's sort of very briefly, that's what a GPT is in a nutshell. And what can we do with it? Well, we can study things like computational power of GPTs, we can study thermodynamics of GPTs, we can study other information processing tasks and interference, and many, many more. But to take one sort of final step back and look at the bigger picture, we can look at sort of the landscape of all possible generalized probabilistic theories. So this is just some schematic picture of this, where we have quantum and classical physics sitting over here, we have more exotic alternatives sitting over here. But we don't want sort of this landscape to just be a very dull landscape where it's just some set of possible theories. We want it to have some structure to it. So this is what these arrows are representing. And in particular, the kind of ways we want to relate physical theories to one another are actually going to be described by monoidal functors between these categories. So say a monoidal functor going from classical physics to quantum physics would be like a useful thing to consider. And these also have a nice string diagrammatic representation as well. So if we have this, then ultimately what we're looking at is the landscape is going to have some sort of two-categorical flavor to it. We've got objects being these GPTs, we've got morphisms of these functors, monoidal functors between GPTs, and then we can consider natural transformations as the two morphisms between those. So once we've taken this step back and have this very sort of broad picture, then there's many further questions that we can study. So for example, we can ask about decoherence from one GPT, such as quantum theory to classical theory, and study when some physical theory would permit decoherence in the emergence of classical world. Similarly, we could ask that some beyond quantum theory should really be able to decohere to quantum theory so that it explains the quantum world that we see in our current experiments. So we can study these ideas as well. And we can study things like contextuality that Ravi was talking about in the last talk, and that's started to be done in these recent papers. Okay, so that was very quick, but I hope I gave some sort of flavor as to the sort of research that goes on here. So to sort of briefly recap, we started by talking about the states of physical systems and thought they could be convex sets. And then we took a step back and defined transformations between these as convex linear maps. And then we saw how we could put together these transformations and states in a particular way to define GPTs as particular kinds of monoidal categories. And then taking a final step back, we see that the overall landscape of the possible GPTs has the structure of some sort of two category. Okay, thanks for your attention. I'm happy to answer any questions that you might have. Thanks.
Thank you, John. I think we have time for a brief question if anyone has one. If not, Yeah, I think there's no questions on the chat. Maybe I'll ask a brief question. So you mentioned at the end is the landscape of GPTs and the fact that they form a 2 category. So has this been, how much of the structure of these 2 categories been explored? And
I think none is the essential answer. I think it really is still in need of
what questions do you see that would?
Yes, so I think what has been studied are things like the maps between GPTs. So these ideas about decoherence and hyperdecoherence have been explored to some extent. So sort of the functors or the morphisms between GPTs have been started to be studied, but only pretty recently, I would say. And then more broadly, things like natural transformations between these functors is something that I don't really know has been explored at all yet. So I think there's sort of a big field out there to be studied. And yeah, if anyone is interested in looking at these kind of things, they should get in contact, because I think there's a lot to do.
Can I ask a follow-up question quickly? So these functors that you draw on the picture here on the right-hand side, just here. So a related question that I thought, like, do you know of any adjunctions that come out of these functors? Are they known, or do they really don't have any adjoints? Or
I think they do.
I mean, can you go backwards? That's what I was asking. You go one way, but can you go backwards?
Yes, sometimes. It depends on the particular functor that you're talking about, I think. So, for example, if I remember right, when you look at decoherence, then I think that decoherence can be thought of as an adjoint pair of functors. In one direction, you sort of have the embedding of classical theory into quantum theory, and then in the other direction, you have decoherence. And if I remember right, those form an adjunction.
Okay, thank you.
Thank you. So I think we should move on to our next talk, which is by John van der Wetering from Radboud and Oxford. And I think you're sharing the wrong. Yeah. Okay. It's working now. And well, he's talking to us about effect algebras. So the floor is yours.
Thank you, and thanks for inviting me. So I'm sitting at a conference in the halls. It might be a bit noisy, so apologies for that in advance. But I hope you can still hear me clearly. So yeah, I'm gonna talk about the thing that John Selby just now didn't talk about, which is the other side of the coin. So instead of state spaces, so what state a system can be in, you can instead ask what properties can we measure of a system. And then we talk about effects, so the things we can know about a system. Okay. So I'm going to very briefly cover Hilbert spaces and quantum logic, and then how we get from automodular lattices of the quantum logic to effect algebras. And then I'm going to show some cool things you can do with effect algebras. Right, so this is sort of the classical picture, like the old school picture of quantum logic. So we describe a quantum system using a complex Hilbert space, and then we model a proposition, so the things we can know about a quantum system by its closed subspaces. So basically, is the quantum state in this subspace of the Hilbert space? Equivalently, we can describe these using positive idempotent operators. And then the question of quantum logic is essentially, okay, what is the structure of the set of projections that you get? So what can we say abstractly about the set of observations you can make about the Hilbert space, about a quantum system? And so the thing that von Neumann settled on was that it is an automodular lattice. So the projections have an order relation, which we can describe in many ways, but one of them that's very intrinsic is, for instance, this one. If we take the product of two projections, we get the smaller projection. There's a minimal element and a maximal element, and it is in fact a complete lattice. So it is a very special type of order. But moreover, it also has a negation operation, because if we have a projection, we can also look at the complement of the projection, so at the other subspace, the alternative subspace. And this makes it an ortholattice, because this negation interacts with the lattice operations in this way. And in fact, this negation satisfies this additional condition, which tells us kind of like how we expect negation to operate. So if P is below Q, then this expression, this negation of P and Q, is sort of the part of Q, the part of P that is below Q, but is like orthogonal to P. And if we join it with P, we get the entirety of Q. So orthogonal lattices were like sort of the cornerstone of quantum logic. But this only talks about sort of sharp observables, so things we can definitely know about a system. But what happens if we want to talk about fuzzy observables, if we want to allow some noise in our measurements, for instance? Well, then instead of talking about projections, we have to talk about effects. So these are operators on the Hilbert space that lie beneath, between the zero operator and the identity. So there are still positive operators, but now they're like below the identity. So projections are a special case of this. These are just more arbitrary operators. And these model generic, noisy measurements of a quantum system. And then we can also take an abstract approach to these, like what is like the abstract structure of a space of effects of a Hilbert space. And a thing that people came up with is an effect algebra. So an effect algebra is a set, E, which has this operation, this binary operation, which is sort of a partial addition operation. So it's commutative and associative, but it's only partially defined. So you can only sometimes add elements. It still has a 0 and a 1 element, so a minimal and a maximum element. And addition with 0 is always defined. And for every A, we have like a unique negation. So I call this A perp. So if we sum A and A perp, we get the 1, we get the maximum element. And this symbol means if A plus 1 is defined, that implies that A equals 0. So we can't add anything to 1 because 1 is the maximum element already. And so, for instance, some examples would be the real unit interval, which has addition, which is only defined when the sum of two elements stays below 1. So you can't keep adding elements. At some point, you run out of space to go up to, and like you can't define addition anymore. And negation is just a regular negation, just 1 minus A. Any orthomodular lattice is an effect algebra, so sort of as a sharp effect algebra, where addition is only defined when two elements are orthogonal, so they are the join is 0, and then we define the sum to be precisely their join. Okay, and another example is any C-star algebra. So if you take the set of subunital positive elements of C-star algebra, with again addition defined when the elements stay below the identity, stay below the unit, sorry, and negation is defined in the way you would expect. So this is sort of the motivating example for C-star algebras, kind of the model for quantum theory, and those form effect algebras. Okay, there's also, because you might think, okay, this definition, it's kind of a bit arbitrary, and to hopefully assuage those fears, there's also a kind of more categorical, nice way to define effect algebras. So we have a category of bounded posets. So those are partial orders which have a 0 and a 1, so a minimum and a maximum element. And then the morphisms are monotone morphisms that preserve 0 and 1. And we have a category of orthomodular posets. So those are not orthomodular lattices. It's slightly weaker, but yeah, you can also make a category of those. And there is, of course, like a forgetful functor from orthomodular posets to bounded posets. And this thing turns out to have a left adjoint. So we can sort of freely add orthomodular structure to a bounded poset. And this is called the Kalmbach extension. And this gives rise to a monad. So we can, like we have a bounded poset and we can sort of add some orthomodular structure to it. And then we can ask, okay, what are the algebras of this construction? And it turns out that those are precisely the effect algebras. So we can think of the effect algebras as sort of this algebraic structure that arises from orthomodular structure. Okay, so that's kind of just an aside of the additional motivation for this structure. Okay, so now I'm going to talk about some use cases for effect algebras. Like what can you do with them? So a thing you can do with them is we can actually generalize the generalized probabilistic theories of the previous talk. So what John Selby talked about, you already presuppose the notion of convexity. Like we presuppose that probabilities are real numbers. And we can ask, okay, is that reasonable? Like, could we maybe think about a sort of exotic universe where even probabilities work differently? We can say, okay, instead of real numbers, we have an effect algebra of probabilities. Yeah, so instead of convex sets, we get effect algebras. And then instead of a GPT, we get a type of category that we call an effectors. It's a bit technical to go into, so I'm not going to do this in this talk. But if you're interested, you can look at Kenta Cho's PhD thesis, Effectors and Categorical Quantum Foundations, who goes into details. Like you can, like many things you can do in GPTs, you can also do in this more abstract world. A related thing you can do with it is you can generalize probabilities. So again, as I said, like instead of real numbers for probabilities, you can use effect algebras. But in fact, you need a bit more structure because in the real unit interval, so the set of probabilities, you also have a multiplication operation. And we also want to model that. So it turns out that the category of effect algebras, it has tensor products, and therefore it also has monoids, so internal monoids in the category. We call this effect monoids. And concretely, an effect monoid is just an effect algebra which has a multiplication operation. So it is an associative, distributive multiplication, satisfying these identities. And we have some examples of those. The real unit interval is sort of the canonical example of that. But also any Boolean algebra, where the addition is the join, but then the multiplication is the meet, and then distributivity is precisely like the condition we ask here. And also, if we have a sort of a continuous set of probabilities, so a set of probabilities can vary over a space, that's also an effect monoid. So this is like the unit interval of a commutative unital C-star algebra, for instance. Okay, so this is just a more general way of talking about probabilities. But in fact, we can recover standard probabilities using this framework. And the way we do this is just adding a little bit more structure. So the unit interval does not just have finite sums, it also has some countable sums. In particular, an infinite sum of probabilities exists when every finite subsum exists. So informally, we can define an omega effect algebra to be an effect algebra where an infinite sum exists, if and only if all the finite subsums exist. Okay. And again, an example would be the real unit interval, but also an omega complete Boolean algebra. There's also an equivalent definition, because this is kind of like this infinitary algebraic definition. There's also an order theoretic definition, which is just that an omega effect algebra is an effect algebra where every increasing sequence has a supremum. So it has a more like a limit kind of feel to it. So this is a result of ours from last year, which says that if you have an omega effect monoid, then it always embeds into a direct sum of an omega complete Boolean algebra and a sort of this like continuous sum of zero of the unit interval. So we get this topological probabilities. For instance, to just demonstrate that this is quite a non-trivial result, a corollary of this result is that omega effect monoids are always commutative. So the multiplication operation is always commutative, which is like, I don't know any easy way to see this, like you really need this classification theorem. But also a nice consequence is that if you just look at irreducible effect monoids, so ones where they're not decomposable into a direct sum, there's only 3 of those. There is just a 0, which sort of represents the inconsistent world, so where probabilities of things are not possible. The deterministic world, where like there's only the Booleans, so where everything holds its certainty or does not hold, and the actual real unit interval. So we can sort of reconstruct probabilities by thinking about irreducible omega effect monoids. It's from abstract, we go to very concrete probabilities. Okay, and then the last thing I want to talk about is we can use effect algebras to rederive quantum theory. So John Selby hinted at this in his talk, that sort of a thing we can do with GPTs is think about, okay, how can we get quantum theory from sort of general assumptions? And I think Alex Wills is going to go into more detail in the next talk. So a way we can do this with effect algebras is, in a different way, is we can think about sequential measurement. So if we have effects on a Hilbert space, we can model the act of first observing A and then observing B using this sequential product operation. And again, we can define an abstract version of this on effect algebras. There's a definition from Gutter and Grichy from 2002. So we say an effect algebra is sequential, a sequential effect algebra, when it has this binary operation, this sequential product operation, satisfying these assumptions. So I'm not really going to go into these, but like if you think a bit about it, like this is sort of saying that if we have 2 commuting measurements, so if A and then B is equal to B and then A, then if we just do classical operations with these commuting operations, they should still commute. So for instance, if we have for instance, if the third axiom here, if A and B commute, then this order of measurement like doesn't really matter. Like we can sort of think about measuring A and then measuring B and then C as sort of measuring A and B together. So we get this sort of like partial associativity. And it turns out that if we think about finite dimensional order unit spaces, so these are a type of ordered vector spaces that occur naturally when you think about GPTs. And we look at this unit interval, and we equip it with a norm-continuous sequential product, then this space must be a Euclidean Jordan algebra, which is a type of algebra that's very close to the things we see in quantum theory. And a bit more abstractly, like if we don't start with this convex structure from the order unit space, if we just think about an effect algebra, but we make it direct to complete so that its order is like very rich, like its order is a DCPO, and we make the sequential product preserve these supremas, then this effect algebra splits up into 3 parts, where the first part is a complete Boolean algebra, so it's completely classical. And the second part is an order unit space. So it is like it has like standard probabilities, it's standardly convex, so we get the standard GPT kind of framework. And the third part is a bit more like ill-behaved. We call this an almost convex effect algebra, and you can kind of see this as sort of a gluing together of convex effect algebras, like sort of a horizontal sum for the people who know what that is. Okay, it's a co-product in the category of effect algebras. Yeah, so like using effect algebra, we can still say quite a lot. We still get all these like nice characterization theorems for these things. Okay, so that's what I wanted to say. So effect algebras are introduced to generalize quantum logic to allow for fuzziness. And then we can use these to talk more abstractly about probabilities. And we can also even use them to rederive quantum mechanics or rederive standard probabilities. Okay, thank you for your attention. And these are some papers if you want to read more about this stuff.
Thank you, John. Should we check again the platform to see if there's any questions there? If not, are there any questions from the other people in the Zoom call?
I have a question.
Yeah.
So, John, I have a question. So the effect algebras that you're talking about, they're more general than the one that those obtained from GPTs, right? So there's that duality relationship from state spaces. We can obtain effect algebras, but there are certain types of effect algebras that maybe occur as one of the components in your decompositions.
So are you asking about the duality, like if there's a duality for effect?
Yeah, I think they are called unit effect algebras, right? That they're coming from state spaces. Is that?
So indeed, the effect algebras you get from GPTs, they are called convex effect algebras because they have a convex action. And we can generalize this duality between state spaces like convex sets and convex effect algebras. We can generalize this because we can think about effect modules. So those are effect algebras that have an action of an effect monoid. And so the canonical example would be the effect monoid of the real numbers, of like the unit interval, and then you get the convex ones. But you can generalize this, and you get sort of a duality between effect modules over a given effect monoid and abstract convex sets over this effect monoid.
Okay, so those abstract convex sets, how should we think about them? So there are no real numbers in those cases, right? But there are these abstract properties of convex spaces. Is that?
So it's so for instance, if you take for the effect monoid the set of continuous functions from a topological space to the unit interval, sort of like a topological space of probabilities, then you would get convex sets still, but now they have like more intricate structure because there's sort of an action of this topological space on. So there's like a bit more rich structure. But for instance, if we take our effect monoids to be the Booleans, well, then the action is trivial because like we can either multiply by 0 or 1, so it doesn't do anything. We just get general effect algebras. So actually, a abstract convex set over the Booleans is just a set. So there's no structure there. Like it's a pointed set because we have a 0. But,
yeah. Okay, thank you.
Maybe I have another question. So I was going to ask something about duality as well, but no, that's been covered more or less. So I'll. You mentioned at some point tensor products of effect algebras, even though it's a bit brief. So I guess John mentioned these as well. So he mentioned like the different versions of like minimal and maximal tensor products and different tensor products that you can have from the sort of GPT side yeah. So what is there to say about it? So are there different notions of tensor product that make sense in effect algebras, and how do they match the? I mean, so for example, you gave an example of if you start from a sister algebra, then you can get the corresponding effect algebra of effects. So how does like what do you call the tensor product of sister algebra of effect algebras? So what does that does that track? So which tensor product of C-star algebras does that track?
So this tensor product that I'm talking about here in the category of vector algebras is the algebraic tensor product. So it's really, when you think about vector spaces, they have this universal property for if you have a bilinear map, then like there's a tensor product as a linear map. It's exactly the same for vector algebras. If you have like a bi-additive map of vector algebras, then the tensor product has a universal property that is like an additive map there. The only caveat being that some vector algebras, the tensor product will be 0. Like it will just be like the singleton set. So it can trivialize, but you always have tensor product with universal property, but it could just be that there's no bi-additive maps and then there's also no non-trivial tensor product. So for C-star algebras, you also would get, I think, the tensor product as vector spaces, I think. But I'm not sure.
And is there a construction on? So is there an operation on effect algebras that sort of capture, like that would sort of capture the C-star algebraic sort of the minimal or the maximal tensor products in C-star algebras?
I think effect algebras are too abstract to say anything meaningful about it. I think you would have to restrict to more well-behaved effect algebras because there's some really weird pathological effect algebras.
True. Okay, thanks. Well, Shihan, you're supposed to take over.
Okay, yeah. Thank you, Bui. Thank you very much to the first 3 speakers. I really enjoyed the talk so far. So our main speaker is Alex Wills from the University of Susquehanna. And we are going to hear about reconstructing and extending quantum theory. So the floor is yours, Alex. Thank you.
Let me try that again. Thank you. Can everybody see the slides okay?
Not yet.
Not yet. Okay. Oh, because I have to actually share it. Here we go. I think it is this one. Let's try. Okay, how's that?
Yeah, looks good.
Okay, good. So yeah, I'm going to begin by thanking Rui and Sihan for putting together this really nice little workshop or special session, and very much also for inviting me to speak. So I want to talk about what is really a very old observation about quantum theory and an equally old attendant problem that arises from that observation. The old observation is that when viewed from certain angles, quantum mechanics looks a lot like a probability calculus, as John was just explaining a little bit ago. But let's review it again anyway. In the simplest version, one associates to a quantum mechanical system a complex Hilbert space, script H, in such a way that the orthonormal bases are interpreted as the outcome sets of possible experiments or measurements. And then the states are represented by density operators, positive trace 1 operators, with the understanding that these assign probabilities to the outcomes of these experiments, which would then be unit vectors, according to the familiar recipe, the so-called Born rule. So the probability of unit vector, but think of it as outcome X in state, represented by density operator W, is the inner product of Wx with X, or equivalently the trace of W times the rank 1 projection associated with X. And that's, of course, fine, and it works wonderfully well, but from a probabilistic perspective, this formal apparatus looks a bit strange, and it looks like it ought to be possible, perhaps, or at least one wants to know whether it's possible to motivate it probabilistically. In other words, the problem is, can we derive this mathematical structure from assumptions that just have a clear operational or probabilistic meaning? I think perhaps the first person to articulate the problem very clearly was George Mackey, who in a very influential survey paper in 1957 observed that it would be very interesting to deduce this structure from what he called a set of physically meaningful, but I think it would be perhaps better to say operationally or probabilistically meaningful and plausible axioms, and then observed that such a derivation was not at that time available. Well, this led to a great deal of work in the ensuing roughly 20 years. And John van de Wetering has already told us a little bit about some of this. Much of it was in the context of quantum logic, in which people tried to provide just exactly such a deduction. And this led to a tremendous amount of really very interesting mathematics. But unfortunately, a lot of the axioms that people brought forward to get the mathematical ball rolling were ultimately not widely seen as all that compelling. And I think it's fair to say that after around 1980, interest in this general project really began to wane. But that changed very dramatically around the turn of this century with the paper of Lucian Hardy's that Ravi mentioned earlier. I think the thing that most occasioned this change was that a lot of people with a background in quantum information theory came to this question with an attitude that said, first of all, finite dimensional systems are perfectly respectable things and worthy of study. And of course, the mathematical going is bound to be a little easier there, but also with an awareness of properties of composite systems, which had perhaps been a little bit slighted in the earlier work. So here's a very incomplete and selective list of some of the many reconstructions of quantum mechanics from probabilistically, operationally, information theoretically well-motivated postulates that have appeared since Hardy's paper. And so I'm going to talk about this general project. And originally I had hopes of surveying several of these, but the talk would have been much longer than 40 minutes. So I'm going to have to be selective. And so I'll focus on the reconstructions of which I myself am guilty. But I will make later some comments on some of the reconstructions in this first line in the sort of style of Lucian Hardy's approach. But of course, we've already heard a little bit about the Barnum-Hilbert result from John Selby, and John van de Wetering has just sketched his really cool reconstruction involving effect algebras. So I won't need to go into those. Okay, so a lot of these reconstructions fit a kind of a standard pattern in which one starts with a broad framework of generalized probabilistic theories. We've heard something about that already. And then one brings in further, more constraining axioms. And here's where there is a lot of variety. It turns out that many different packages of axioms will all lead to the same place, which isn't exactly quantum mechanics, but rather a class of probabilistic models based on Euclidean Jordan algebras, which are close to quantum mechanics, but include some more exotic things as well. Once you've gotten that close to quantum mechanics, there's then a sort of well-known, well-trodden path that takes you, takes you all the way to quantum mechanics over the complex field. And that's to add a single principle called local tomography, which I'll describe a little bit later. It has to do with how systems combine. But this also indicates a direction in which you might look for generalizations of quantum mechanics. Specifically, just don't take that last step and just look at Euclidean Jordan algebras. And it turns out there are some very interesting things you can say about probabilistic theories based on those. And I'll discuss that if I have time at the end of the talk. That's joint work with Howard Barnum and Matthew Braden. Okay, so I want to review this framework of generalized probabilistic theories, although I'll be kind of covering somewhat the same ground that John Selby did. But I want to approach things just a tiny bit differently. Rather than starting with an abstract convex set as a state space, I'm going to start with something more concrete, what's called a test space, which mathematically is just a collection of sets, a non-empty set of non-empty sets, a hypergraph, script M, but with this interpretation that each of the sets in the collection is to be understood as the outcome set of some measurement or experiment, or to use a more neutral term, test. If I let capital X stand for the union of all of these tests, all of these outcome sets, then it's natural to define a probability weight on the test space to be a function, alpha here, that assigns probabilities two outcomes in such a way that these probabilities add up to 1 over all the outcomes of each experiment, of each test. And then a probabilistic model is simply a pair that consists of a test space, a catalog of available measurements, and some designated selected set, capital omega, of probability weights, which we will call the states of the model. And that allows for quite a lot of generality. At this stage, I'm not assuming anything much about M or omega. So many, many possibilities are embraced by this framework. Here's a sort of a toy example just to illustrate the definitions for those who haven't seen them before. If we consider this little hypergraph here, capital X, the set of outcomes is the set of nodes, and the set of tests are the tests are the sets of nodes along each of the 3 signs of the figure. So there's a blue test, a green test, a red test. And here are some sample probability weights. The only constraint is that I have to have numbers between 0 and 1 that add up to 1 along each side of the figure, as I do in each of these examples. So a probabilistic model based on this test space would just be this test space and some probability weights on it, say maybe these 2. Okay, so let's see here. Yeah, so let's look at some other examples. A very simple classical example, the sort of thing you might present to your students in Statistics 101, would consist of a single test, maybe a finite one, and a single probability weight, alpha. The quantum model that we talked about at the beginning fits this framework very well. You take for your test space the set of orthonormal bases of your Hilbert space, and for omega, the state space, all the probability weights that arise from density operators according to the Born rule. It's worth mentioning in passing that if the dimension of H is at least 3, then this is all the probability weights. That's the content of Gleason's theorem, a very deep and celebrated result that I won't actually need. Okay, the set of all probability weights on a test space is convex. Certainly the weighted average of probability weights is another probability weight. And as long as all of the tests are finite sets, it's also closed as a subset of the space of interval valued functions on the outcome set in the product topology, and therefore compact. Now I'm going to make some standing assumptions just to simplify the discussion from here on. One is I'm going to assume that tests are indeed finite sets, and I'm going to assume that omega is indeed a convex compact set, if not take its closed convex hull in here. And finally, I'm going to assume that the state spaces are all, for today, finite dimensional, since finite dimensional quantum mechanics is sort of the target. Okay, a little notation that will be helpful. If I want to indicate a model by a capital letter, let's say A, by a single letter like capital A here, then I'll write M of A for A's test space, omega of A for omega's state space, and so on. Later in the talk, it's going to be useful to equip a model with a little bit more structure, specifically a designated group, which I'll write as G of A, if the model's name is A, of symmetries, by which I mean permutations of the outcome set that permute the tests and permute the states. Okay, this framework can be linearized in a very natural way. Let's let V of A, where A is a model, be the span of A's state space in the big space of all real valued functions on the outcome set. That's ordered pointwise on X of A. But another way to say that is that the positive cone of V of A as an ordered vector space is just the set of non-negative multiples of states. We can picture that this way somewhat figuratively. Here is the 0 function on big X. Here are the states hovering above that. Here's the cone. The part of the cone that lies below the state space, the set of multiples of states by coefficients that are between 0 and 1, are useful things to consider. I'm going to call them subnormalized states. Okay, this construction has a wonderful property, and that is that if you have any affine, that is convex combination preserving functional from the state space to the unit interval, then such a functional extends in a unique way to a linear functional on the entire space V of A. Such functionals are called effects, and as was discussed earlier, we can think of them as at least mathematically possible measurement outcomes consistent with the rest of the structure, interpreting the value of the functional at a state alpha as the probability of that virtual or mathematically possible outcome occurring. In particular, there's always a unique unit effect, which I'll write as U sub A, that assigns value 1 to every state. In other words, it's an effect that always happens, and that exists just because there is a constant affine functional with value 1 on omega. Now, every actual outcome, every one of the designated outcomes in X of A, corresponds to an effect just by evaluation, and it's often convenient to identify outcomes with these corresponding effects, treating X of A as a subset of the dual of V of A. In quantum mechanics, this would amount to replacing unit vectors as outcomes by the corresponding rank 1 projections. Another ordered vector space that I'm going to want to use later on is something I call script E of A. It's the dual of V of A as a vector space, but rather than using the dual cone, which would be the set of positive linear functionals on V of A, we're only going to look at those linear functionals that are linear combinations of outcome effects with non-negative coefficients. In general, that's a smaller cone than the dual cone, but it's noteworthy that for the quantum models we talked about earlier, all three of these vector spaces coincide as ordered vector spaces, and they're all, in fact, isomorphic to the space of self-adjoint operators on the Hilbert space H. In infinite dimensions, I should add, these are all three different. V of A would be the self-adjoint trace class, its dual would be the set of all bounded self-adjoint operators, and E of A would be the set of finite rank self-adjoint operators. But in our context, they're all going to be essentially the same. Now, one of the things we want to do with probabilistic models, as both Johns were discussing, is to construct composite models. And a good starting point is to talk about the notion of a joint state, or a little bit more accurately, a joint non-signaling state for a couple of models A and B. That's going to be a function that assigns joint probabilities to outcomes of A and of B, to ordered pairs of outcomes, in such a way that those joint probabilities add up to 1 over all the pairs of outcomes coming from a pair of tests, but with a further restriction, which is that if we partially evaluate at X and then think of the result as a function of Y, an outcome of B, that should be a subnormalized state of B, an element of V of B plus. And similarly, in the other order, we should get a subnormalized state of A when we partially evaluate at an outcome of B. This condition guarantees that the marginal states that you get by summing over a test in one argument or the other are well defined. They don't depend on which test you sum over. That's often called the no signaling condition, because it prevents us from sending statistical information from A to B or vice versa, simply by choosing to make one measurement or another. And it also guarantees that these marginal states belong to the right state spaces. Now, by a non-signaling composite of two models, I mean a model, say AB, if A and B are the models, together with a mapping that takes a pair of outcomes, one from A, one from B, and combines them into not necessarily a product outcome, but a product effect. So an element of this space here. That gives me a little extra flexibility, which in some cases you need. The constraints are that, first of all, if we define omega of X comma Y to be omega of the joint or product effect XY, that should define a joint state in the sense of the previous slide. And secondly, if I have two states, one from alpha, one from A rather, one from B, I should be able to realize that as a state of the composite system just by multiplying like this. So in effect, I should be able to prepare states of A and states of B independently. Any joint state on AB is always going to extend to a positive linear functional from, this should be a script E of A cross script E of B to R, so to a positive bilinear form on script E of A and script E of B, and that'll be important later. Okay, there's one final ingredient in this general framework, which is the notion of a process. For me, a process from A to B is a positive linear mapping from V of A to V of B that satisfies this condition, which basically says that states are mapped to subnormalized states. I don't necessarily want to preserve normalization because there may be some cases in which, with some probability, the process fails. An extreme case would be where the system is somehow destroyed. An equivalent way to say all of this is that the dual mapping from the dual of V of B to that of the dual of V of A has to take effects to effects. Okay, and then finally, once we've got a clear understanding of what we mean by a probabilistic model, a probabilistic theory is just going to be, as John Selby was saying, a symmetric monoidal category, but in my case of concrete probabilistic models and processes, and with a monoidal product given in terms of non-signaling composites. So whatever the monoidal product is, it has to give you a non-signaling composite. The target example for us would be finite dimensional quantum theory, maybe without super selection rules, just to keep life simple, which would consist of quantum models with maybe trace non-increasing completely positive maps as processes, and with a composite compositional structure that's given in the obvious way by taking the tensor product of the Hilbert spaces. Okay, now I want to talk about probabilistic models associated with Jordan algebras, and at least one of many available ways in which you can motivate these from simpler principles. People have mentioned Euclidean Jordan algebras. Since I have a little bit more time, I'll describe what these are. These are finite dimensional real inner product spaces, bold E here, with a commutative binary operation with a unit called the Jordan product, satisfying this identity called the Jordan identity, and also playing nicely with the inner product in this sense that you see here. Examples of such things are the spaces of Hermitian n by n matrices over any of the classical division rings, or if n is equal to 3, and only in that case, you can use the octonions. And in each of these cases, you take, for the Jordan product, the normalized anti-commutator, and for the inner product, the normalized trace inner product, and then you get a Euclidean Jordan algebra. You can also look at things called spin factors, which are just the Euclidean spaces Rn plus 1, here factored as R cross Rn, with this Jordan product that you see here. And it turns out that's basically it, because Jordan, von Neumann, and Wigner proved in 1934 that all Euclidean Jordan algebras are direct sums of those of these types. Because Hermitian sets of Hermitian matrices over R, C, or H can be thought of as the sets of observables of finite dimensional real complex or quaternionic quantum systems, this structure puts us at least in the neighborhood of finite dimensional quantum mechanics. And it's also interesting that associated with a Jordan model, you've got a probabilistic model in a natural way. Any Euclidean Jordan algebra is also an ordered vector space with a positive cone given by Jordan squares, things of the form A dot A. And you can define then a probabilistic model by taking as your test space the set of Jordan frames, which are sets of minimal idempotents that sum to 1, or equivalently maximal sets of pairwise orthogonal idempotents. And you can take for your states the set of positive linear functionals on E that are normalized so that they assign the value 1 to the Jordan unit. And then, of course, those will sum up to 1 on each Jordan frame. So we have a probabilistic model. There's a spectral theorem for Euclidean Jordan algebras, according to which every element of the algebra can be expanded as a sum of scalar multiples of minimal idempotence coming from a Jordan frame. And using that, you can show that the ordered vector space script E of this Jordan model, as I'll call it, is isomorphic as an ordered vector space to the Jordan algebra you started with this cone of squares. So a step in the direction of quantum mechanics would be to characterize Jordan models probabilistically. And here's one way we can do that. If you have any finite dimensional ordered real vector space with positive cone as indicated here and with an inner product, then you say that, that this space is self-dual if the vectors that have a non-negative inner product with every element of the positive cone are precisely the elements of the positive cone. And you say that such an ordered vector space is homogeneous if the group of order automorphisms, that is to say linear automorphisms that are positive and have positive inverses, acts transitively on the interior of the cone. Well, rather spectacularly, Max Kucher and independently Ernst Winberg proved in the late 50s and early 60s that that ordered finite dimensional real vector spaces with these two properties, homogeneous and self-dual, ordered vector spaces are precisely those that arise from Euclidean Jordan algebras. So that gives us a strategy, which is find conditions on a probabilistic model so that maybe this space script E of A is self-dual, in which case we'll have to find an inner product on it. And maybe the space V of A is homogeneous. I shift to V of A because homogeneity looks like it should involve processes which act on spaces of this type. And then finally, you'd like to tie these two spaces together by showing they're isomorphic, maybe with respect to the self-dualizing inner product on E of A. That should take you to Euclidean Jordan algebras. So to get an idea of how we might go about doing these things, let's go back and look at standard finite dimensional quantum mechanics. If we have an n-dimensional complex Hilbert space, H, and E is the space of self-adjoint operators thereon, that's self-dual as an ordered vector space with respect to the trace inner product, as I already mentioned. And what's really cool about this and instructive about this is that the normalized trace inner product is actually a state. It's a bipartite state on H tensor, the conjugate of H. In fact, it's a pure state given by this expression here. You recognize this as the analog for H tensor, H conjugate of the maximally entangled or EPR state. Now, this state has, in addition to its purity, which it won't be so important for me, it has a tremendously interesting correlational property. It perfectly and uniformly correlates every orthonormal basis, that is, every measurement on H with its counterpart on H conjugate. If you work out the Born rule probability of seeing outcome X and the corresponding outcome X conjugate in this state, it's just 1 over n. Okay, so this is something that we can say in the language of GPTs, in the language of probabilistic models. Suppose we have a model A that, like a quantum model, is uniform, meaning that all of its tests have a common size, a common number of outcomes. Let's call that number of outcomes n. That's called the rank of the model. By a conjugate for such a uniform model, I mean another model, which I'll call A bar, together with an isomorphism that lets us pair up the outcomes. We'll just write X bar for the outcome corresponding to X, and a joint state, a joint non-signaling state, eta sub A, which I'll call a correlator, that has two properties. First, like the normalized trace inner product, it uniformly and perfectly correlates every measurement on A with the counterpart on A conjugate by assigning these probabilities to diagonal pairs X bar. And secondly, I want to assume that it's symmetric in the sense that you see here. This is a benign condition because if I don't have this condition, but I do have condition A, I can just average A to A with its transpose, and I still will have a correlator, and it will be symmetric. Now, notice that the marginals of this correlator are going to be the maximally mixed states with uniform probability 1 over n on every outcome. And therefore, these are states of A and of A conjugate, respectively. Okay, a few additional conditions. Suppose that a model is, rather call a model sharp if every outcome has probability 1 in a unique state. This is certainly a property of both classical and quantum models. And call it spectral if additionally every state breaks up as a convex combination of these special delta X states summed over the outcomes of some test. This is, by the way, related to but not identical to the kind of spectrality that shows up in the Barnum-Hilbert result that John Southey was talking about. All Jordan models are sharp and, in particular, spectral. And here's a lemma that's actually not that hard to prove once you've taken on board the various definitions. If A is spectral and it has a conjugate, then the correlator of that conjugate, thought of as a bilinear form, so I can evaluate at arbitrary elements of script E of A on each side here, that defines an inner product on E of A, and moreover, that inner product is automatically self-dualizing, and with respect to that inner product, script E of A is isomorphic to V of A. So that brings us almost all the way to where we want to go, except we have to motivate spectrality. I don't think that's a completely obvious condition. And more importantly, we have to motivate homogeneity. We have to show that V of A is homogeneous. There are a lot of ways of doing both of those things, many, many ways that I know of. But let me just talk about one of them that I have a particular fondness for. It involves the notion of what I call a filter. The term filter is used for many different things in the literature. This is what I mean. A filter is a process. A filter for a test E is a process from V of A to itself, such that for every outcome of the measurement and for every state, if you apply the filter to the state, the result assigns to outcome X a probability that is the same probability it would have had in state alpha, except multiplied by some attenuating factor T sub X. I think this picture might help get the idea across. Here I imagine some sort of Stern-Gerlach-like measurement, and the outcomes should be thought of maybe as detectors. And the idea of a filter is that by applying the filter to the state prior to the measurement, you get the same effect as if you had gone through and sort of turned down the gain on each detector by some factor independently for each detector. It's certainly possible to do this always in classical cases, and it's also possible to do it in quantum mechanics. If you have any effect on your Hilbert space, positive operator between 0 and 1, then this operator from density operators to density operators is a filter for any eigenbasis of A. And notice, by the way, it's also an invertible mapping if the effect A is non-singular. I'm going to say that a state can be prepared by a filter if you can always find some coefficient P, perhaps think of it as a probability, so that the filter applied to the uniform probability weight gives you back the target state up to that scaling. So you get a subnormalized state perhaps, but one with, so to say, the same shape as the original state. Now, in quantum theory, I can always do this, because I could take W to be the maximally mixed state, and I could take A to be a density operator representing my target state, which is an effect in particular. If every interior state, or equivalently, if every state that is strictly positive on all the outcomes can be prepared by a reversible filter, then it's pretty easy to see that V of A is homogeneous. But we can actually say a little bit more. There's a slightly stronger result. If A has a conjugate, let's agree that a filter is symmetric with respect to that conjugate if it obeys this condition. So I can apply it, here I'm applying the dual version of the filter, but if I can apply the filter on either side to A or to A conjugate with the same effect, then the filter's symmetric. And it turns out that if A has a conjugate and if every interior state can be prepared by a reversible symmetric filter, then not only is A homogeneous, it's automatically spectral. And therefore, by the previous lemma, A is going to be a Jordan model. And conversely, every Jordan model has all of these features. So this theorem actually characterizes Jordan models in an operationally meaningful or probabilistically meaningful way. I'm going to go very briefly because I suspect I may be running short of time, and just mention that another approach to doing this goes by way of what's called a submodel or a subspace, more usually in the literature, sorry. There's a construction, which I won't read through, assigning to every outcome X of a model a sort of restricted subspace or submodel. And many of the reconstructions of quantum mechanics in the tradition of Hardy's paper, these in particular, make use of a version of what I call the strong subspace postulate, which says you have a probabilistic theory, and for every model in the theory and every outcome of that model, the restricted subspace model is also in your theory. And furthermore, any process on the submodel extends to a process on the full model whose dual process fixes the outcome. There's a weaker version in which only symmetries are required to extend, but I think this is equally plausible. This is a very strong condition, or a very powerful condition, maybe I should say. If we call a model compact to mean that the outcome set is compact, maybe in script E of A, and symmetric if it's got a designated group of symmetries that act transitively on the outcomes, then you can show that any probabilistic theory consisting of symmetric, compact models in which every model has a conjugate and in which this strong subspace property holds consists entirely of irreducible Jordan models. So that's another route to Jordan models that you can take. Okay, so now let me talk about what you can do with Jordan models. This is a joint work, as I mentioned, with Howard Barnum and Matthew Graydon. If you have a monoidal probabilistic theory, you say that it's locally tomographic if its states are all determined by their associated joint probability weights, meaning if omega 1 and omega 2, two states of AB, agree on product effects, then they're actually identical. This is equivalent, in fact, to saying that as a vector space, V of AB is just the tensor product of V of A and V of B, at least in finite dimensions. And you can say something similar in infinite dimensions with an appropriate completion of the tensor product, but I won't go into that. Now, finite dimensional quantum mechanics over the complex field satisfies local tomography. That's been observed over and over, and it's often used to separate it from quantum mechanics over the reals or the quaternions, which are not locally tomographic, as you can verify on dimensional grounds. In fact, we have a result. This is something I came up with Howard Barnum some years ago, but it actually goes back to work of Harald Hanche Olsen in the 80s. If you have a locally tomographic theory that consists of Jordan models and it contains the simplest possible complex quantum system, the qubit, then it actually has to consist entirely of complex quantum models. It's a subtheory of standard finite dimensional quantum mechanics. Okay, but what if we give up on local tomography? I mean, what if we don't embrace it? After all, real and quaternionic quantum theory are theories are sort of at least semi-respectable theories. Changing notation, let me start writing A indifferently for a Jordan model and the corresponding EJA, Euclidean Jordan algebra. Then an embedded Euclidean Jordan algebra is a pair consisting of Euclidean Jordan algebra and an enveloping finite dimensional complex star algebra with A sitting inside the self-adjoint part of that as a sub-Jordan algebra, Jordan subalgebra of MA self-adjoint. If I have two such embedded Jordan algebras, then there's a natural way of forming their tensor product. Just look at the tensor product of A and B inside the tensor product of their enveloping star algebras and take the Jordan subalgebra of that tensor product of matrix algebras generated by A tensor B. I'll call this the canonical product of A and B. It turns out this canonical product is associative and is naturally associative, and it also gives you a proper non-signaling composite of Jordan models. And it turns out more, you can build symmetric monoidal categories this way. If you have a class of embedded EJAs that is closed under this canonical product, then calling a linear mapping from the ambient matrix algebra of A to that of B, completely Jordan preserving, if for any third EJA in the category or in this class, phi tensor, the identity, preserves the canonical tensor product, sends that of A and C to that of B and C. These mappings turn strip C into a symmetric monoidal category under the canonical tensor product. And a really interesting example of this is to look at those finite dimensional Jordan algebras that show up as the algebras of fixed points of star involutions on finite dimensional complex star algebras. It turns out that that collection is closed under the canonical product, and therefore using the CJP construction, we get a symmetric monoidal category. It actually turns out to be compact closed. If you are familiar with the lingo, you know that's an important condition. Its irreducible members are precisely the self-adjoint parts of real complex and quaternionic matrix algebras. So we have those three types of quantum systems all sort of playing together. And they compose, according to this table here, of which the interesting part, which I'll sort of try to highlight here, which I guess I can't actually, the interesting part is this middle entry. Everything else sort of composes as you might expect, but the composite of two standard finite dimensional complex quantum mechanical systems is not what you would expect. It's the direct sum of two copies of what you'd expect. So the price for unifying these three kinds of quantum systems seems to be that with the complex systems combine in such a way as to produce an extra classical bit, a two-valued superselection rule. The significance of that is still under study, but it seems really interesting. And I suspect I'm out of time, so I will stop there with a list of references. Thank you very much.
Thank you, Alex. Thank you very much. Any questions for Alex? So I think I need to check the website. Okay. Okay, no questions here. Okay, any questions from the audience?
Yeah, kind of a question. Thanks, Alex, for your very interesting talk. And I would, yeah, I was going to ask one thing. So I think at the beginning you kind of mentioned that a lot of the extra sort of the renewal of interest in these kind of questions kind of came by through quantum information, and especially with a focus on finite dimensional systems and composite systems. And I guess my question goes the other way. So does any of that kind of give us, say, something about infinite dimensional systems, or can we use any of the stuff that we've learned?
Yes, I think so. I want to say that I don't completely agree that that finite dimensional systems are just a matter of convenience. I think there's actually a great deal of analytical spade work that still has to be done to get everything to work properly in infinite dimensions. But there's a good deal of work that was done even back in the 70s and 80s on the structure of especially ordered Banach spaces and dual pairs of ordered Banach spaces by people working actually ultimately on foundations of quantum mechanics in that idiom that can be brought to bear. There are also some interesting tools that are still available from the older quantum logic literature, which does apply in infinite dimensional cases, which I think bear a second look. We might not be enamored of all of the assumptions that went into quantum mechanics, but I think a lot of the quantum logic, but I think a lot of the tools that were developed are still quite useful. So yes, I think there's a lot that can be done, but there's some work that has to be done.
Thank you.
You're welcome.
Okay. Are there any other questions? Otherwise, I think it's time to end the session. It seems like so. So thank you very much to all the speakers. It was a great pleasure to have you all. So, Rui, do you have anything to add, or shall we close the session?
No, I don't think I don't have anything to add.
Okay.
Yes. I mean, if any of the speakers, I think we have more time for questions or discussion if anyone else wants to. Not a lot of time, maybe 5 minutes or so.
I think I'm pretty good, but I do want to say thank you again. This was a lot of fun, and I want to thank all the other speakers. Actually, I learned some interesting things from all 3 talks. So, thanks.
Yep, I second that. I think from all 4 talks.
Thanks.
Thanks to you all for agreeing to come and to speak to us.
Well, I mean, who doesn't want to go to Portugal?
Well, exactly. Well, next time maybe we can do it in a actually in Portugal rather than
it'd be good. All right. Well, thanks everybody again. So take care.
Thank you. Okay. Thank you very much, everyone.
Thanks, everyone.
Good to see everybody.
Yeah, thanks, everyone.